Okay, I've got another little theorem that I want to look at. This is Tim Brzezinski put together this particular GeoGebra sketch that I want to use here. What we have here is we have three parallel lines like this. I can change how they go like this, how they tilt. I have a line going through them, marking off some line segments here from A to B and B to C. So we have line A, C with B between them. And then we have another line going through D and F, marking off some line segments here, D to E and then E to F. So E is between F and D. And these may be, closer here or longer here. So we could measure these links, and there's something that we should notice about them, is that they're actually proportional. For example, if this one here was maybe say twice as long as this one here, this one's twice as long as that one there. Okay, so how can we see this? Well, the first thing that he wants us to notice is by the F property, we get these two are congruent there. Well, first of all, if these happen to be parallel, you got some nice parallelograms, so those would be the same length and these would be the same length, and so your proportions are clearly the same there. But if they're not the same, like it's out here or out here, then I should be able to take this, let's say it goes like that, for example. Well, let's say it's here. Then I can make a parallel through A parallel to this, like this. Now we've got a parallelogram here, so these are congruent and these are congruent. But notice that because of these here, angles being congruent, and of course they share an angle here, we have some triangles here, a triangle there, and then a triangle here that are similar. And that gives us these are proportional to these here, but these are the same as the ones over here. So that's basically our proof there. Here's a write-up of it formally. We're given lines L, M, and N, which are parallel to each other. This one's L, M, and the N's on the bottom. So the L is the line going through A and D, N and M is the line going through B and E, N is the line going through C and F. And then we have two transversals, AC and DF. And B is between A and C, and E is between here, such that, of course, they're on these lines here. Okay, so we can always set that up, and we have a couple proportionalities here. The length of A to B divided by the length from A to C is the same as the length from D to E divided by the length D to F. And another way to look at it is this way: the length A to B divided by the length B to C is the same as going from D to E, dividing that by E to F. So this marks out proportional lengths. Case 1, S and T are parallel. Then we're going to have parallelograms. This little shape right here would not be like it looks here, but would actually be a parallelogram. I showed you that just a minute ago. AB, ED, which means opposite sides would be congruent there and there. AB would be equal to DE. And then ACFD would be a parallelogram too. And if that's the case, AC would be congruent to DF. Let's see, ACFD. Yeah, oh, I've written that one twice. I meant to say BCFE for the second one. And from that one, we get BC congruent to EF. And the last one, ACFD, that's congruent to sides there, opposite sides, so AC congruent to DF. And so just substituting in, we can see that AB over AC is the same, exactly the same thing as DE over DF. And then AB over BC would be the same thing as DE over EF. Okay, so this is a substitution there. Now, if S and T are not parallel, construct AE prime, the line through that's parallel to the line that goes through D and F, which is S. Okay, this one over here is T, this is S. And so the E prime is on this line here, BE, that was M, and E double prime is on N, which is the line down here, and E prime is between A and E double prime, so those are all on the same line like that. That just sets up the way we have it in their picture. And then by the parallelogram theorem, once again, opposite sides are congruent, so AE equals, or AE prime is the same length as D to E. We have a parallelogram here, we have a parallelogram here, so E prime to E double prime is the same length as E to F, and then the big length A to E double prime is the same from D to F. Let's see if I said that right. I think I have the same typo I had up here. And so I think we got all that right. And now, but we have the F property that says that these two angles here are the same size, congruent. Angle ABE prime is congruent to angle BCE double prime because we have these two parallel lines here, these two being parallel, and those are corresponding angles. That's the F property. It says they have to be congruent from our transversal parallel lines theorem. So now we have these two triangles, of course, share angle A. Maybe I should say that. So angle A is shared. So this triangle ABE prime is similar to triangle ACE prime. That one, similar to the big one there. And of course, then what does that mean? That means that this side, corresponding sides are proportional. So AB over AC is equal to AE prime over AE double prime, which is what I have right here. AB over AC, AE prime over AE double prime. Yeah, that's what I've got right there. But then now we can substitute. What do we have? We have AE double prime is DF, and AE prime okay, so just substituting that in. Once again, AE prime is DE, so substitute that, and AE double prime, there it is DF, and so that's the second part. That's the first part we were trying to prove, and we can get from here to here from any because if we get this proportion implies this proportion here. And that's just some algebra basically, and the properties of between that are going on here. Well, we can get from this. Actually, what we get is from this triangle, if they're similar, one of the things that we saw from our earlier lemma is that we did back before the AA theorem at all, is we showed that if this was true because of the betweenness relationships and so forth, we found that if they're similar, that we get AB is to BC as AE prime is to E prime, E double prime. Okay, right here, this relationship. And then this is just substituting again. AE double prime or AE prime is DE, and AE or E prime, E double prime right here is EF. And so that works out to give us that. And that completes our proof. And this can be extended to other things, not just, three lines cut by two transversals, but you could have 4 or 5 or 6 lines cut by transversals. As long as the original lines are all parallel and you have two transversals, they're going to cut off proportional lengths. Or you could have 3 lines cut by more than two transversals. They're going to cut off proportional lengths. So this could generalize pretty nicely as well.